The next talk is from Pierre-François Gimenez, who is coming from, yeah, it's not ready, but I like to talk, so I can fill the blanks. Don't worry. He's a research scientist at INRIA, French laboratory in Brittany, I believe. And he's going to talk about some formal methods application today. The talk is titled Towards Programming Language Free of Injection-Based Vulnerabilities by Design. Good luck with this.
Yes, I changed the title yesterday, so something that's more easy to understand. Right?
Okay. Thank you.
Hello, everyone. So this is a joint work with Eric Alata. We worked at last CNRS and now works at Intel. And this work was also supported by PEP-REV. So you probably know about injection attacks. The basic idea is that it uses a user input to modify the semantics of a sentence. Let's have some example. So it was an RATP ad. Maybe you saw it a few years ago. So the name of the subway station is Jules Geoffrin. And they added some words at the beginning and the end of that to make a new sentence, à mon Jules Geoffrin baiser, which changed the semantics of the Jules Geoffrin part. So this is a kind of injection, but of course I will talk about software injection. So the most kind of well-known injection or SQL injection. For example, here you have some template with two blanks, one for login, one for password. Of course, I, as a developer, expect someone to put his login and password, but an attacker will probably put admin in the first blank and quote or 1 = 1 -- in the second one. And if the attack works, then the access is granted. So this is the kind of injection attack you're probably most familiar with. But in fact, it's not just about SQL. Many CVEs can be found in programming languages, such as Bash with common injection, also some CVE about JavaScript, Python, also format like JSON, XML, protocols such as SMTP, LDAP, and markup languages like HTML or CSS. So this threat is very common and very serious. And typically, when we talk about injections, the typical answer is, okay, but nowadays it's not a problem anymore because we have frameworks, they handle that very correctly, and for SQL, for example, there are proper statement. And okay, it's not possible for all languages. For example, you don't have proper statement for bash command, for example. It adds another overhead. And what if there is a user that do not know about this issue, do not have time or skill to correct it? But most of the time, people say, okay, it's not a big deal anymore. We know how to solve it, so okay, who cares? But I would argue that the root issue here, it doesn't come from careless developers. It does not come from insecure framework. Injection are possible because of the language themselves. So we took a different approach, a scientific approach. We defined the problem, we analyze the properties, and our goal is to fix this problem at the root directly. Okay, so I will have an example so it's clearer. I will use the LDAP protocol, or a very subset of it. You probably know LDAP. It's a protocol used for search in directory services, and it's regularly used for authentication. So there are a few examples. So on the first one, for example, you have a condition with an AND here with two elements. UID must be equal to foo, and password must be equal to bar. Here you have a condition with 3 elements. You can see a not here. You also have a OR condition, and so on and so on. So as a researcher, we can describe this grammar with this language with a grammar, which is presented here. So how does it work? This grammar is used to derive a sentence, a query here. So we start with the symbol S, and you can rewrite this symbol with some production rule. For example, here, S can be rewritten into parentheses and L parentheses. And then, okay, parentheses is the end of the symbol, but L is something I can further detail. So L can be replaced with LS, and I can continue with these rules to continue my derivation until I have some complete sentence. And in fact, the sentence is in the leaf of a tree. So here, this derivation with this production rule, lead to the query and UID is foo and password is bar. So I will make some definitions so it's clearer for everyone. So I will call query, it's a complete command. For example, an LDAP query, a JSON file, network packet, and so on. And I will call template a query that is incomplete. It is typically what is written by the developer. For example, here, the developer writes end UID is some blank and password is 1234. So because there is a blank, I will call that a template. And an injection, I will call injection anything that can be included in this template. So in this definition, injection are not always malicious. There are benign, legitimate injection and malicious ones. And we propose to modelize this malicious injection with the fact that probably the developer has an intent in mind when they write this template. Probably the intent, for example, that the user puts a condition, a string, and so on. So we will denote this intent with a symbol of a grammar, for example, L or S, and so on. And we will say that the injection is legitimate if what is put by the user can be explained, can be derived from this symbol. So as an example, if as its template here, USD is blank, password is 1234. The intent of the developer is I expect a string, S. So for example, a legitimate injection will be root, but a malicious injection will be not just one string, but for example here, foo, parentheses, parentheses, lock equal bar, which leads to a correct sentence, a correct query, but it is considered malicious because it does not fit the intent of the developer. And now we define two properties of security, intent equivalence and intent security. Intent equivalence means, okay, I have some template with a prefix P and a suffix S, and I want to check whether they can only accept legitimate injection. Is it safe, this template? For example, for LDAP, in this example here, you can see that the final parenthesis is missing, and if the developer wants the user to put the parentheses here, we can show that there is no way the user can put anything else in this place. It will not just be syntactically correct query. So this template is secure. It is completely useless, but it is secure. But the second one is not secure because I have shown just before, we can inject this kind of injection, which show that it is not secure. And we have some reference to formal grammar. We can show that, okay, it is possible most of the time with automated method to check whether a template is secure or not, whether it can accept malicious input or not. And then we're going to go to the next step. Is it possible to have some languages that can only produce this safe, this secure templates? We know, for example, that for LDAP it is not the case, of course, because I can easily create a template that is vulnerable. So our question was, okay, but can we check for any grammar if it is secure or not? And we found that globally, no, almost all languages will be vulnerable. Okay, but it was a lot of talks about some grammars and so on, but I did not give you any intuition about why is there this vulnerability and what can we do about it. So I will focus on two results. First, with the fact that for most of the programming language we use, we have some form of regular languages into it. Typically, as soon as you have some lists with an unknown number of elements, you will have some repeated part. For example, here for SQL, you can select one attribute, 2 or 3, and so on. So you can have any number of attributes. So it can be expressed as a regular expression here, attribute, comma, repeated any number of times, and then an attribute. And as soon as you have this repeated form with a star, the attacker can add some element. So, for example, if the the developer wanted just one attribute, the attacker can put one attribute, comma, another attribute. So as soon as we have this kind of structure in the grammar, we know it is not secure. And this kind of pattern is everywhere. For example, the second one for SQL query semicolon query, I mean, it is the base of the piggybacked injection that we see most of the time. Same for OS command. We can just change them with semicolon and command. And in fact, many, many languages have this kind of structure. As soon as there is this structure, we know that an injection is possible. Okay, and then another result is that if you have two blanks in the template, then we show that no language is safe. No programming language is safe. For example, here I have a LDAP query with two blanks, one for UID and one for password. This is a legitimate injection with some foo and bar. And this is a malicious injection. This one, maybe you already know it. It's equivalent to or1 equal 1 for SQL. It's a way to bypass authentication. And if I show you the version tree, on the left, this is the legitimate injection. And I have this blue part here, which is written by the developer. And due to the attack, the attacker will change how this password equal is interpreted. It will change in semantics. In fact, it will move across the tree. So this kind of attacks, they're just the way grammar works, context-free grammar works, and we cannot avoid them. So we know that if we allow for two blanks in templates, we cannot secure it. Okay, so what I told you so far is that languages are insecure. Okay, great news. We already all know that, but how can we leverage what we learned to secure them, which is probably the most important. So first, we cannot prove that some grammar is secure, but we could create new languages that are secure by design. And in fact, we will show some patterns to make them secure. So everything I will tell is for only one blank, because we know that for two blanks, it's always doomed. So there is a big, big theorem about what is sufficient to be secure. I won't detail it, but I will show some special cases that are easier to understand. The first pattern I would like to show is called open-close, and the idea that if every rule starts and ends with a unique symbol, then the grammar is intent secure. Let's show a very simple example. Okay, I showed you before that as soon as we have a list with some regular pattern, it will be vulnerable. So the grammar of a list will look like that. Either it's I have a list L, either it's one element, so L is returned to E, or more than one element, so is E, comma, and the rest of the list. If I have a template, for example, here E1, comma, blank, comma, E2, we can inject it with like E, or E, comma, E prime. So it is vulnerable, of course. And I will slightly change it by putting unique tag at the end of the start of each rule. So here we have some square bracket for the first rule and some brace bracket for the second one. And then I will just put a query, a template, that just asks for one element. And here you can see that the attacker cannot put anything but just one element, because this brace bracket is only for the last element of a list. So we cannot put more than one element. Okay, but if we have a more complex here query, so we ask the user to put one element, you can try to find an injection here. But the problem is that if you want to put, for example, 3, comma 3, you will need to put some square brackets, opening square brackets, but you will also need to put some closing brackets. But you cannot do that because it's at the end. The only way you could do that is if you can inject in the last element, but the last element is protected with this brace bracket. So in fact, here, you cannot do some injection. And so with a small cost, arguably this is more verbose, but we know that this particular language is secure against injection with only one blank. Okay, and now another design pattern, which is if we assume the injection cannot target the tags, so the start of the end of the rules, then it is enough to have a unique opening tag. So let's go back to LDAP. This is our grammar before, and we'll slightly change it. So here you can see that, okay, the parentheses here are curly brackets, and we use brace bracket for the last element of a list, and square brackets for that. And then this template that was insecure I will rewrite it slightly by adding some new samples. And once again, I invite you to try to find an injection here. But you won't be able to. Okay, so I hope it was clear. The main takeaway is that for us, injection vulnerability come from the language themselves. And we can try to put some protection above of that, but the main vulnerability is directly baked into what is the language itself. As soon as some regularized patterns with star, it will be injectable. And we also show that all programming languages are vulnerable with 2 injection points, sadly. And one interesting thing is that the more complex the grammar, the more secure it can be, which is a bit of in contrario to what we see generally in security. And we can create some design patterns for languages to make them secure by design for when blank. This was a small example for LDAP, but of course it works for everything else. Thank you.
Thank you, Pierre. We have time for questions.
I actually have one question for you if nobody wants to try it out. Yeah, so you've shown an example from LDAP. So is it theoretical protection you could put there, or is it something you try to implement in LDAP?
Sadly, we could not take this work further because we have other projects. I would really love to actually implement it and create not just a toy example, but more some real life. I think there is also a question of how to design language, because this is maybe effective, but this is very ugly to use as a developer, and I think we can do much better. So it's not planned, but if someone here is very motivated about it, please come to me, and I will be delighted to work on that with you.
And I don't know if it was clear to the audience, but when he said he showed something, there is an actual theorem and demonstration about that.
No question? Okay, so thank you, Pef, again. Thank you.